Welcome to the space where science meets the stillness of the soul. This is not only a place for you to relax after a long day, but also a slow journey into the deepest mysteries of humanity and the universe. Tonight, we will step into a question that has kept scientists and philosophers debating for decades. Could consciousness originate from the strange world of quantum physics? Stay with me until the end of the video, because this story not only challenges curiosity, but may also change the way you see yourself. If you enjoy gentle yet profound explorations like this, please subscribe to the channel and turn on the notification bell so you won't miss the next journeys. Your companionship and support are the motivation that helps the channel continue to grow, so that every night we can discover another secret of the universe together. When we mention consciousness, the first thing that often comes to mind is not formulas or diagrams, but deeply personal experiences. The warmth of a morning, the aroma of coffee, or the vague nostalgia when hearing a familiar song again. It is something so close that it feels obvious, yet at the same time, it is something science has not fully grasped. Neuroscientists can point out how neurons fire, biologists can track how neurotransmitters spread, but all those numbers still do not answer the big question. How does a cold, lifeless matter give rise to this vibrant inner world? This is the starting point of what is called the hard problem of consciousness. Philosopher David Chalmers distinguished between the easy problems, such as explaining how the brain processes signals or controls behavior, and the hard problem, namely how subjective experience emerges from physical activity. This hard problem makes consciousness a mystery far beyond ordinary biological mechanisms. You can imagine, studying the brain is like disassembling a computer to look at its circuits, wires, and electrical currents. But even if you understand every technical detail, you still cannot pinpoint where the experience of playing a game or the feeling of joy or sadness resides. There remains a gap that current science cannot yet fill. It is precisely this gap that has led some thinkers to turn to a field that seems unrelated: quantum physics. This is the discipline that describes the microscopic world, where fundamental particles like electrons and photons do not behave according to our everyday intuition. In the quantum world, a particle can exist in a superposition, both here and there, both a wave and a particle, until a measurement takes place. Two particles separated by light years can still be entangled, sharing states instantaneously. These phenomena, although confirmed by countless experiments, still amaze us and raise the question: what is reality really? When we put these two mysteries together, on one side consciousness, on the other quantum physics, a bold hypothesis emerges. Could our consciousness be related to the quantum world, or even be a quantum phenomenon itself? Some scientists have proposed that the brain may function like a natural quantum computer, exploiting superpositions and entanglement to process information in ways beyond imagination. If this were true, it could explain why humans are capable of creativity, imagination, or such complex emotional experiences. Some other thinkers go even further. They suggest that the very act of observation, central to quantum mechanics, requires the presence of a conscious mind. From this perspective, consciousness is not just a byproduct of the brain, but could be a fundamental component of the universe itself. However, not everyone agrees. Most neuroscientists reject the quantum consciousness hypothesis. They point out that the brain is too warm and noisy an environment for fragile quantum effects to last long. Quantum superpositions typically survive only under ultra-cold conditions, isolated from their surroundings. Therefore, according to them, linking consciousness to quantum physics is more likely a poetic analogy than scientific reality. Even so, the allure of this idea remains strong, not because it has been proven, but because it resonates with our intuition that there is something in consciousness that goes beyond neural equations. It also sparks imagination, connecting two beautiful mysteries: the human mind and the nature of the universe. Perhaps this is why the hypothesis continues to live on in debates, in popular culture, and in those quiet moments before sleep, when we wonder, are we merely biological brains or somehow a deeper part of the quantum universe? To approach this question fairly, we need to listen to both sides: the current scientific evidence and the curiosity that drives us to search for new answers. The upcoming journey will take you through experiments, theories, and philosophical speculations. Not to definitively prove that consciousness is quantum, but to see more clearly why this hypothesis is both doubted and irresistibly fascinating. As you sit and listen, let your mind slowly open, like someone strolling in the quiet night, where each step brings us closer to a secret. Whatever the final answer may be, the act of asking the question itself is enough to evoke awe and humility before the vastness of reality. After all, consciousness is not only an object of study, but also the only tool we have to perceive the world. When we ask about consciousness, it is also the moment consciousness asks about itself, a strange circle, but also the most beautiful journey the human intellect has ever begun. Perhaps one of the most remarkable events in this later stage is when two seemingly unrelated figures together revive the connection between the brain and quantum physics. One is physicist Roger Penrose, a Nobel laureate with groundbreaking work on black holes and the nature of space-time, and the other is anesthesiologist Stuart Hameroff, a specialist in consciousness from a clinical perspective. In the 1990s, they proposed a controversial hypothesis that also sparked a wave of intense discussion, the OR theory, orchestrated objective reduction. According to Penrose, quantum mechanics has an important gap. The equations can describe the superposition state of a particle, but they do not explain why and how that state collapses into a specific outcome. Instead of viewing collapse as a purely measurement-driven process caused by the observer, he argued that spacetime itself has a microstructure, and this very structure may force the wave function to collapse. This was a bold idea. Rather than bringing consciousness in as a mysterious factor, Penrose treated collapse as an objective phenomenon of nature, and this very phenomenon could be closely related to perception. Hameroff, from a medical perspective, added an important detail. He pointed out that inside neurons are structures called microtubules. These tiny protein tubes are not merely the skeleton of the cell, but may function as sophisticated channels of information processing. Hameroff proposed that microtubules could be the place where quantum states are sustained in the brain, something many traditional neuroscientists considered impossible because the brain is too hot, too noisy, and too chaotic to preserve the fragility of quantum states. But Hameroff and Penrose countered that microtubules possess special properties that could protect and amplify quantum effects. When the ideas of Penrose and Hameroff are combined, we get the following picture. The brain is not merely a classical neural machine, but may be harnessing the strangest laws of the universe to generate consciousness. Each moment of awareness, each spark of presence in the mind, may coincide with a quantum collapse occurring inside microtubules. Consciousness in this hypothesis is not an illusion or a byproduct of electrical impulses, but a phenomenon tied to the deepest structures of reality. However, the OR hypothesis is not easily accepted. Many scientists argue that sustaining quantum states in the brain is nearly impossible, since even the smallest interaction with the environment could destroy the fragility of superpositions. Critics claim the theory is too speculative and supported by too little experimental evidence. Yet some recent experiments suggest that quantum effects may play a role in biology, for example, in plant photosynthesis, or in the way migratory birds navigate using Earth's magnetic field. If life can exploit quantum phenomena in other biological systems, could the brain do the same? Whatever the answer, the appeal of the Penrose-Hameroff hypothesis lies in the philosophical doorway it opens. If consciousness is truly linked to fundamental quantum processes, then awareness is no longer just a local biological phenomenon happening inside the skull. It becomes part of the universe itself, interwoven into the fabric of space-time. And if so, when we experience the feeling of I exist, perhaps we are touching the very layer of the universe where matter and mind are no longer separate. On the other hand, most neuroscientists argue that none of this is necessary. They contend that the brain, with its 86 billion neurons, each capable of thousands of connections, is complex enough to give rise to consciousness without requiring quantum physics. They liken adding quantum mechanics to the brain to using a sledgehammer to kill a fly, an unnecessary complication. Modern artificial neural network models, which simulate neural connections, have already shown astonishing capabilities, from speech recognition and language translation to generating images and music. For them, this demonstrates that consciousness, or at least its components, can be built from classical computational rules. And yet there remains a crucial distinction. Machines can mimic behavior, but do they actually feel anything? This is exactly the hard problem emphasized by David Chalmers. Why do subjective experiences arise from electrochemical processes? Why, when dopamine is released, do we not merely act like reactive machines but actually feel joy? Here, supporters of the quantum hypothesis see an opportunity. Perhaps only by embedding consciousness within the fundamental structure of nature can we explain the existence of qualia, the inner experiences that cannot be reduced to equations. Whether in agreement or opposition, it is clear that quantum theories of consciousness have ignited the imagination of millions. They evoke the sense that the mind is not merely a byproduct of the brain, but may be a window into the strangeness of the universe. That does not mean science has found the answer, but it makes the conversation vibrant, connecting physics, biology, and philosophy in an ongoing dialogue with no end in sight. And perhaps it is precisely this lack of closure that makes the story compelling. If science had closed all doors, we would have nothing left to dream about. But as long as hypotheses like OR remain, as long as great minds continue to debate, we still have reasons to keep asking, where does consciousness truly come from? And that, in the stillness of a late night, feels like a gentle invitation for you to reflect, to let go, and to let your mind drift along with the waves of the universe. One of the things that makes the quantum brain hypothesis so controversial yet so compelling is the intersection of two seemingly distant worlds, the rigor of physics and the ambiguity of consciousness. Here, classical neuroscience often describes the brain as an extremely sophisticated biological machine, operating according to predictable electrochemical laws. But the quantum hypothesis opens up another perspective, that beneath this familiar picture lies a deeper layer of activity, where the laws of probability and uncertainty shape the flow of the mind. Supporters of this view often emphasize the concept of quantum coherence. In physics, coherence is the ability to maintain a superposition state before collapsing into a single outcome. Normally, in a noisy environment like the brain, where billions of chemical reactions and thermal vibrations occur continuously, coherence is thought to be nearly impossible to sustain. However, surprising discoveries in biology show that nature sometimes has the ability to preserve quantum phenomena. Photosynthesis is the classic example. Light energy appears to be transferred by exploring multiple pathways simultaneously, a behavior that can only be explained by superposition. Migratory birds may also orient themselves thanks to quantum entanglement effects in their retinas. If plants and birds have already harnessed quantum mechanics to survive, could the brain, a far more complex system, have evolved to exploit it as well? Skeptics, however, argue that this is too great a leap. The brain is indeed miraculous, but there is no direct evidence that microtubules or other cellular structures actually sustain superposition states. The complexity of the brain may be sufficient to explain consciousness without invoking quantum mechanics. From this perspective, phenomena such as creativity, memory, or emotions can be seen as emergent properties of vast neural networks without needing to posit an additional, hard-to-verify quantum layer. Furthermore, experiments in quantum physics typically require ultra-cold, nearly isolated environments to avoid decoherence, conditions the human brain clearly does not have. Even so, the appeal of the quantum brain hypothesis comes not only from its potential to explain consciousness, but also from the way it touches on humanity's age-old aspirations. For thousands of years, philosophy has asked, where does consciousness come from? Is it independent of matter? And is the mind linked to the deepest nature of the universe? When quantum mechanics appeared with paradoxes such as uncertainty, superposition, and the role of the observer, it seemed to unintentionally evoke parallels with our very own inner experience. For many, consciousness and quantum mechanics are not only parallel in science, but also like two mirrors reflecting one another in philosophy. Imagine a moment when you face an important decision. In front of you is not a straight path, but overlapping possibilities. Your mind hesitates, wavers, and finally a choice is made. This feeling, from the sparkle of possibilities to the collapse into a single decision, is reminiscent of the behavior of particles in quantum experiments. Though it is only a metaphor, it is precisely this resonance that makes the hypothesis so captivating. It suggests that free will may not be merely an illusion, but perhaps an expression of the fundamental uncertainty of the universe. Another aspect that makes this hypothesis enduring is its cultural and imaginative power. It has become a subject for literature, film, and popular philosophical discussions. The idea that every creative thought, every spark of inspiration, even the experience of love or intuition could be the echo of quantum vibrations in the brain sounds like a bridge between science and spirituality. While serious physicists and neuroscientists are often cautious about such connections, it is undeniable that they stir curiosity and urge us to keep searching. From a scientific perspective, attempts at verification are still ongoing. Some research groups have sought to detect traces of quantum vibrations in microtubules or to test the effects of anesthetics on these structures. The results so far remain inconclusive, but the very process of asking these questions has expanded the frontiers of neuroscience and quantum biology. Even if the quantum brain hypothesis ultimately proves false, the journey still has value. It forces scientists to think differently, to experiment with new tools, and to accept that the mystery of consciousness may require unprecedented theoretical frameworks. What is important to remember is that science progresses not only through correct answers, but also through bold questions. Penrose and Hameroff's OR may still be far from broad acceptance, but it reminds us of something. Consciousness is not only a scientific problem, but also a search for meaning. Just as quantum mechanics once shook the foundations of classical physics, the quantum brain hypothesis, whether successful or not, enriches the intellectual landscape of humanity. Perhaps the greatest value of this hypothesis does not lie in whether it is absolutely correct, but in the way it keeps our imagination alive. It compels us to ask, is the mind not merely a byproduct of matter, but also a participant in the fundamental structure of reality? The answer is still ahead, but the very act of daring to ask that question is already a testament to the spirit of science, a spirit always yearning to cross the boundaries of the known to step into the unknown. Although the skeptical stance carries weight and is supported by much empirical evidence, the appeal of the quantum consciousness hypothesis is not easily extinguished. In fact, it exists as one of the most vivid examples of science and philosophy intertwining, where the limits of current data open doors for the imagination to soar. There is an undeniable allure in the idea that the human mind does not merely reflect the world, but is woven from the same fundamental fabric that makes up the stars, elementary particles, and spacetime itself. Here we touch upon something important. Even if quantum brain theory is not correct in the strict scientific sense, it remains true in another sense, the sense of inspiration and expanded perspective. Throughout history, bold hypotheses have often played the role of sparks, igniting experiments and research that, without them, science might have slowed. The atomic theory was once considered pure speculation for thousands of years, until modern physics provided evidence. The germ theory was also once dismissed before the microscope revealed a vibrant microscopic world. From this perspective, the OR theory, or quantum consciousness, can be seen not as a conclusion, but as a beacon, illuminating new directions in neuroscience and biophysics research. Another important factor that keeps this hypothesis rooted in the collective imagination is its resonance with questions of free will and creativity. Humans have always yearned for the feeling that they are not absolutely bound by the cold mechanical laws. When neuroscience suggests that every decision may simply be the result of a deterministic chain of biochemical reactions, many feel deprived of part of their humanity. Here, quantum mechanics provides a loophole, a possibility that within the indeterminacy of quantum states, there is room for true freedom. That notion, even without solid evidence, touches on a deep longing that we are more than thinking neural machines. Not stopping at philosophy, science itself also provides some thought-provoking pieces. As mentioned, photosynthesis and bird navigation suggest that biological systems can, in some cases, maintain quantum coherence in warm and complex environments. This does not prove that the brain operates in the same way, but it opens up the possibility that nature has found subtle protective mechanisms to harness fragile quantum effects. If plants and birds can, then the idea that the brain, the most complex organ known, might also exploit something similar is not entirely unreasonable. This leads to a more important argument. Sometimes the value of a hypothesis does not lie in whether it is right or wrong, but in whether it compels us to ask new questions. Quantum consciousness, even if ultimately rejected, has motivated many researchers to seek quantum effects in biology. It encourages interdisciplinary investigations, where physics, chemistry, neuroscience, and philosophy meet. These dialogues not only generate data, but also enrich human intellect. However, it is also necessary to emphasize an important truth. Quantum consciousness has not yet provided clear empirical predictions. This is the key point that makes many scientists cautious. A strong scientific theory is not only beautiful in concept, but must also be testable. It must propose specific conditions under which we can say, if this phenomenon is not observed, the theory is wrong. OR and similar hypotheses still lack such criteria. This makes them easily regarded as pseudoscientific philosophy rather than science. And it is precisely here that we see the interesting tension, an idea that both nourishes imagination and shakes empirical standards. Another aspect worth considering is the nature of mystery itself. Perhaps what makes quantum consciousness attractive is not the promise of an answer, but the reminder that many questions remain unsolved. In a world where science has explained most phenomena once considered miraculous, consciousness still stands as a final fortress, challenging our comprehensive understanding. Does it truly require new physics, or simply a deeper dive into what we already know? This question, even without an immediate answer, is powerful enough to stimulate the curiosity of the entire community. And finally, perhaps the greatest value of quantum consciousness lies in its symbolic power. It reminds us that science is not just about building dry equations, but also about the journey of imagination. The idea that within every neuron there might be hidden quantum glimmers makes us view the brain with different eyes, not only as a biological organ, but as a stage where the deepest laws of the universe are revealed. Even if it is later proven wrong, this hypothesis will already have fulfilled a precious role, nurturing wonder and urging humanity to keep asking questions. In this light, it can be said that the debate around quantum consciousness is not a scientific failure, but a vivid expression of science itself. For science is not merely a collection of facts, but also the spirit of daring to venture into uncharted territories. And if consciousness truly is a quantum mystery, then that journey of discovery has only just begun. When discussing the observer problem, we are truly standing before one of the greatest turning points in the history of science, where pure physics meets profound philosophy. The question of whether consciousness plays a role in wave function collapse has fascinated generations because it suggests that human awareness is not merely a byproduct of biological processes, but may be directly connected to the very nature of reality. For some scientists and philosophers, this idea resembles a bridge between mind and universe, a promise that in every moment of awareness we are not merely observing, but also co-creating the world. However, the allure of this hypothesis does not mean it is widely accepted. On the contrary, most modern physicists argue that assigning consciousness the role of activating reality is a confusion of language and concepts. In the original equations, the observer is simply any system that interacts with a quantum system, a detector, a photon, even the surrounding air. Decoherence has shown that quantum states do not require a conscious mind in order to collapse. Rather, it is the interaction with the environment that suffices to erase fragile superpositions. Consciousness, in this interpretation, is not the cause, but one of countless consequences of the quantum classical dance. Alongside this, there still exists a line of thought that dismissing the role of consciousness entirely is too hasty. Indeed, something compels us when faced with the idea that awareness, the most subjective human experience, could be linked to the most fundamental layer of physics. The history of science has seen many ideas that seemed mystical yet later opened new pathways. For this reason, the quantum consciousness hypothesis persists, partly because it sparks imagination, and partly because it has not yet been definitively disproven. Some scholars suggest that we may be approaching the issue from the wrong angle. Instead of asking, does consciousness collapse the wave function? We should ask, might some aspect of quantum mechanics provide a new language to describe conscious experience? This approach is less absolute, but perhaps more practical. For example, superposition could serve as a useful metaphor to describe the ambiguous, potential rich state of creative thinking. Or entanglement might illuminate how neural processes distributed across the brain still coordinate coherently to create a unified experience. While not necessarily equivalent to the existence of a quantum brain, such images still carry evocative power. On a deeper level, the observer problem also touches on a classical philosophical issue. Does reality exist independently of the observer, or does it only exist in the process of being experienced? This is not only a scientific question, but a long standing dialogue between materialism and idealism, between the objective world and the subjective world. Quantum mechanics, with its ambiguous and paradoxical language, seems to breathe new life into these debates. Somehow, it makes us feel that the world is not just a blindly operating machine, but that there is room for the participation of mind. Interestingly, even the most skeptical scientists cannot deny the symbolic power of this idea. Imagine, every moment we look at a particle, a star, or another person, we may be helping to realize its state. In this picture, consciousness is no longer a faint echo of neurons, but the spotlight illuminating the universe. Even if only metaphorical, this remains one of the most powerful images ever produced by science and philosophy. Of course, from metaphor to empirical proof is a very large gap. And this is precisely where physicists warn of the danger of turning science into disguised mysticism. A scientific hypothesis, however captivating, must still generate testable predictions. Placing consciousness at the center of quantum mechanics has so far yielded no experiment capable of distinguishing it from other explanations. Without evidence, such an idea risks remaining forever suspended in the fog between science and philosophy. Yet, this uncertainty is not entirely useless. In many cases, bold hypotheses are guiding lights, opening new fields of research. The question of the role of consciousness in quantum theory has forced physicists to think more deeply about the nature of measurement, the relationship between system and environment, and the limits of mathematical description. It was through such debates that decoherence theory emerged, explaining many previously obscure phenomena. Once again, history shows that even wrong hypotheses can create value if they inspire the right directions. Perhaps, instead of striving to find a definitive answer, we should accept that the observer problem reveals a terrain where science and philosophy intersect. There, the search for truth is not only about data and formulas, but also about imagination, about the human need to connect subjective experience with the objective picture of the universe. Consciousness may not be the cause of wave function collapse, but it is certainly the reason we care about this question in the first place. And perhaps it is precisely here that this mystery holds lasting value. Uh, it reminds us that science is not only a journey toward the right answer, but also a journey of expanding vision, allowing us to see the world and ourselves in new lights. The observer problem, whether resolved or not, remains a mirror reflecting the subtle relationship between humans and the universe. We are both products of physical laws and the ones who question them. In that duality lies a beauty that can be felt without needing to be proven. The measurement problem in quantum mechanics can be seen as a mirror, reflecting the way humans struggle with the limits of knowledge. Each interpretation, from Copenhagen, many worlds, to pilot wave theory, resembles an effort to weave a coherent story from the scattered threads of mathematics. They differ in detail, but share the same aspiration to find an answer to the paradox that quantum theory has thrown in our face. And it is precisely at that crossroads that the question of consciousness once again has the opportunity to return, like a shadow that never completely disappears from the picture. One reason why consciousness is tied to the measurement problem is because it represents an irreducible experience. We can describe the world with equations, with experiments, but the experience of seeing a result cannot be excluded from the story. When we say that a particle appears here, that is always tied to someone or something recording that event. It is precisely that act of recording that turns a possibility into a fact. So is consciousness merely a passive witness, or does it somehow participate in the game? Supporters of the quantum consciousness hypothesis often point out that superposition and entanglement bear strange similarities to the flow of thoughts in the brain. At the neuronal level, the brain operates as a complex network where information can be processed in parallel, multiple possibilities coexisting before a decision is made. Some scientists, such as Roger Penrose and Stuart Hameroff, have proposed that microtubules in brain cells may sustain quantum states, and that consciousness arises from this. Though this hypothesis is hotly debated and lacks convincing evidence, it still sparks curiosity. Could the secret of the mind lie at the same level as the secret of the electron? On the other hand, skeptics warn that attributing quantum properties to the brain is merely a way of borrowing the prestige of physics to tackle a tough problem in neuroscience. In reality, the temperature and moist environment of the human brain makes sustaining coherent quantum states nearly impossible. Quantum effects, if they exist, would decohere quickly. Moreover, even if quantum phenomena were present in the brain, that would not automatically solve the question of what consciousness is. Current evidence shows that classical processes such as electrical and chemical signaling are sufficient to explain most neural activity. Interestingly, this debate reveals another truth. Consciousness, regardless of its physical origin, is always central to the way humans interpret the universe. It is we who wonder why a particle chooses one outcome instead of another. It is we who write equations and then grow dissatisfied when they refuse to tell us a complete story. In this sense, consciousness does not necessarily have to be the physical cause of wave function collapse, but it is certainly the philosophical cause of the entire debate. From this perspective, the observer problem is no longer simply a scientific question, but a mirror reflecting humanity's deep desire, the desire to find ourselves in the universe. Perhaps we are not satisfied imagining reality as nothing more than a lifeless stream of mathematics. We want to believe there is some connection between our fragile subjective experience and the grand objective structure out there. The idea that consciousness collapses the wave function is an expression of that longing. Yet history of science shows that such longings often need to be tempered in the fire of experiment. Theories may captivate the mind, but will quickly fade if not grounded in evidence. And so far, no experiment has proven that consciousness has a special role in quantum mechanics. On the contrary, all measurement phenomena can be explained by physical interaction between the quantum system and its environment. This does not mean that consciousness is unimportant, only that it is not a necessary piece in the quantum mechanism. But even if we rule out the quantum consciousness hypothesis, a great mystery remains. Why do we, finite beings, have the ability to use our minds to touch the deepest layers of reality? Isn't this precisely what makes consciousness so miraculous? Even if it does not collapse the wave function, consciousness is still the only tool that allows us to perceive, to question, and to seek answers. In this context, the role of the observer is no longer at the physical level, but at the philosophical level. We do not shape the universe by looking at it, but by desiring to understand it. Therefore, instead of seeing the observer problem as a failure, we may see it as a reminder that science and philosophy always walk hand in hand. Science provides extraordinarily precise predictions, but it is philosophy that asks, what does this mean? And sometimes the gap between prediction and meaning is precisely where imagination blossoms. Quantum mechanics is not just a set of computational tools, but also a rich treasury of metaphors for reflecting on the relationship between self and universe. Thus, even when the scientific community affirms that consciousness is not needed for wave function collapse, the opposite idea continues to live on in the human mind, as a modern myth. It is not only a question of physics, but a symbol of an undying longing to find ourselves in the vast universe, to believe that in our gaze lies something that helps create the world. Perhaps it is only an illusion, but it is precisely such illusions that have driven us further along the path of discovery. While many neuroscientists maintain that consciousness is an emergent product of the brain's complexity, some other researchers argue that there are still aspects that a purely biological approach has not fully explained. A clear example is subjective experience, what philosophers call qualia. No one can objectively prove whether the red you see is identical to the red I see. Imaging tools, EEGs, or neural models can tell us which regions of the brain light up when you look at a flower, but they do not answer why that experience feels red rather than just being a lifeless stream of visual data. This is the hard problem of consciousness, a term coined by philosopher David Chalmers, and it still has no complete explanation within the framework of classical science. It is precisely in this gap that quantum mechanics is often invited to the discussion. Some researchers, such as Roger Penrose and Stuart Hameroff, have proposed that microtubules in neurons may be where quantum phenomena occur, thereby giving rise to consciousness. This hypothesis is called orchestrated objective reduction, OR. Though controversial, it breathed new life into the debate, for it suggests that the brain is not merely a gigantic electrochemical machine, but could also be a sophisticated quantum system, where superposed states bring depth to human experience. However, to date, experimental evidence for this hypothesis remains unconvincing, and many scientists see it as an overextension of physics into biology. Yet, even if we reject the quantum consciousness hypothesis, the debate still raises an important value. Consciousness is the intersection between science and philosophy, between measurable data and questions of meaning. Neuroscientific theories can describe the activity patterns of brain cells, but they cannot replace the question, why is there subjective experience here, and not just cold information processing? The presence of that question makes consciousness one of the most fascinating mysteries humanity has ever faced. Another interesting point is that when we compare consciousness to other complex phenomena in nature, we see a familiar motif. The deeper we study, the more surprises we find. Molecular biology once showed that life is the result of extremely intricate chains of chemical reactions, not some mysterious vital force. Astronomy once discarded the geocentric view, opening up a vast universe in which Earth is just a speck of dust. Perhaps consciousness will follow the same trajectory, from being an untouchable mystery, gradually becoming a phenomenon that can be analyzed, modeled, and even artificially recreated. If that happens, consciousness will no longer be a quantum secret, but another step forward in the long history of scientific discovery. However, skepticism still holds value because it reminds us that self-awareness cannot be reduced solely to equations or brain images. When we sit in a quiet room, close our eyes, and let our minds wander, we do not merely feel neural impulses, but a stream of memories, imagination, and emotions. That is what makes humans special, the ability to reflect on themselves. And perhaps, regardless of how science explains it, that subjective experience will always retain its sacredness in life. Some scientists suggest that we may never fully explain consciousness in the conventional sense. Instead, perhaps we will learn how to work with consciousness, much like we worked with gravity before Newton wrote down its law. Humans long knew that heavy objects fall to the ground and used that rule in construction, transportation, farming, long before any physical equation existed. Consciousness is similar. Even without fully understanding its mechanism, we can still learn how to nurture, train, and harness it for creativity, healing, and connection. It is at this point that science meets philosophy, and philosophy meets art. For consciousness is not only an object of study, but also the dwelling place of poetry, music, memory, and love. A purely scientific theory, no matter how accurate, may explain how neurons fire, but it cannot replace the experience of being moved by a beautiful piece of music or the feeling of longing when thinking of someone who has passed away. That is why, even when neuroscientists affirm that consciousness does not require quantum mechanics, the public remains captivated by the idea of quantum consciousness. It is not just a scientific hypothesis, but also a sacred metaphor for the profound connection between human beings and the universe. Perhaps instead of asking, is consciousness a quantum mystery, the more important question is, why do we want it to be a quantum mystery? Is it because we long for a direct connection between our fragile minds and the deepest laws of the universe? Is it because consciousness, so intimate and personal, seems to demand a more grandiose foundation to reflect its extraordinary nature? If so, then the very question itself already says much about humanity, that we are not only searching for explanations, but also searching for meaning. And thus, the journey to explore consciousness continues along two parallel paths, one scientific, where each small step adds up to a clearer picture, and one philosophical artistic, where humans never cease to reflect, to question, and to transform lived experience into language, sound, and image. These two paths may never fully converge, but the distance between them creates a space for imagination, for wonder, and for the belief that much still remains unknown. While experiments are still struggling to find quantum evidence in the brain, a parallel picture is gradually forming. The evolution of classical neuroscience increasingly strengthens the power of explanations that require no metaphysical element. Here, we see an interesting opposition. On one side, OR researchers and similar hypotheses still hope to find traces of quantum coherence in microtubules, as if they were the secret bridge between elementary particles and consciousness. On the other, experimental neuroscientists continue to uncover the precision and reliability of electrochemical mechanisms that already explain nearly all the functions of cognition. Between the two is not a solid wall, but an open border where the question, where does consciousness come from, still echoes without an answer. One of the strongest counter-arguments against the quantum consciousness hypothesis is the problem of biological noise. In the brain's environment, high temperatures and constant collisions of countless molecules make any delicate quantum state, if it exists, easily collapse within an instant. Physicists call this decoherence. To maintain quantum coherence long enough to produce conscious experience, the brain would have to resemble a giant quantum machine perfectly isolated, a condition biological evolution never prioritized. On the contrary, nature has chosen resilience, redundancy, and repetition. A neural network can lose thousands of connections and still maintain function, while a quantum system may collapse entirely from even the smallest disturbance. This argument makes many feel that the quantum consciousness theory, while beautiful, is too fragile to stand firm. Yet, from this very point, supporters find opportunity. They point out that nature has often astonished us with mechanisms once thought impossible. Photosynthesis, for example, has been shown to use short-term quantum coherence to optimize energy transfer. Birds may orient themselves thanks to quantum effects in the retina. If evolution can harness quantum mechanics in such small organisms, why couldn't the brain, one of the most complex systems ever to exist, do the same at a higher level? Thus, the debate continues like a prolonged chess game, where each scientific move opens new questions instead of closing the match. In fact, it is precisely the absence of a clear answer that makes this topic fascinating. People are drawn to the idea that consciousness, the thing we experience every second, might be tied to the deepest laws of the universe. It evokes a poetic sense that in each of our thoughts, in each flash of memory or moment of awareness, there may exist a quantum melody resonating, connecting the individual mind to the vast fabric of the cosmos. No matter how science argues against it, the allure of this image is not easily extinguished, for it touches humanity's long-standing yearning, the belief that our minds are not merely random products of matter, but carry within them a sacredness beyond pure mechanics. But science, as usual, demands patience. Current experiments show that microtubules can oscillate in complex ways and that anesthetics can interfere with them, but declaring this as evidence for quantum consciousness is still premature. On the other hand, neuroscience continually demonstrates that changes in neurochemistry, electrical stimulation, or even sleep modulation all directly and predictably affect consciousness. These results are repeatable, verifiable, and reproducible, while quantum evidence is often vague and difficult to replicate. This disparity in certainty is what makes the majority of the scientific community lean toward classical explanations. Nevertheless, this should not be seen as a failure of the quantum consciousness perspective. On the contrary, it reflects a core principle of knowledge. Bold hypotheses, even when unproven, still play the role of expanding the boundaries of imagination. They force us to ask questions, to experiment, to seek new tools. OR may be right, or it may never be confirmed, but it has kept alive the dialogue between physics and neuroscience, between philosophy and science. In that process, we not only learn more about consciousness, but also about the very limits of the methods of knowing that we use. One key point needs emphasis. Regardless of which direction prevails, the search itself has value. If consciousness truly emerges from classical complexity, the achievement will be a detailed map of the brain, where every thought can be explained by neural activity. If consciousness is connected to quantum mechanics, such a discovery will force us to rewrite our understanding of both mind and universe. Both scenarios are revolutionary, and both enrich the human story. While awaiting evidence, we can view quantum consciousness as a powerful metaphor. It reminds us that the mind may be so complex that even the most sophisticated theories have not yet grasped it fully. It shows that knowledge is not just a straight road toward truth, but a labyrinth full of turns, where each dead end opens a new perspective on ourselves. The quantum metaphor for consciousness, even if not scientifically correct, may still be spiritually correct. It says that consciousness is multidimensional, nonlinear, elusive, and always suggestive, just like the strange nature of the universe we live in. Looking back, we realize that what matters is not a definitive conclusion, but how the journey of seeking reflects humanity's deepest aspirations. We want to understand ourselves, to know whether thoughts and emotions have a place in the grand picture of reality. We want to be sure that consciousness is not just an illusion, but a real part of the universe. For this reason, whatever the final result, the dialogue about consciousness and quantum will continue, as proof that there are questions that not only need answers, but also need to be asked again and again to keep wonder and the thirst for knowledge alive within us.